Hello everyone. In today's session, I'm going to discuss one another important concepts of discrete mathematics, which is graph isomorphic, or we can say isomorphic graphs. Okay, so this is having a wide application in various domain of CS as well as in AI as well as in electronics and telecommunication. It is used in biomedicals. It is used as one of the cryptography tool. It is used for image recognition, biometrics, finger sensor, face sensor. Okay, so it do have a variety of applications. Now let us try to understand what exactly we mean from graph isomorphic or isomorphism. Basically, two graphs, or in general, we can say two shapes are uh, isomorphic to each other if they do have each and every characteristic same between them, except the shape. Shape may differing as per the individual, but except the shape, if everything else between two graphs or two shapes or two faces are same, we call them as a identical graph shape or figures or faces. Okay, so isomorphic interchangeably used as a similar, identical. Okay, so synonyms of isomorphisms can be considered as identical, similar, but not in terms of shapes. Okay, but not in terms of shape. If two graphs is having each and everything between them as same, the graphs are said to be identical or isomorphic. The shape may differ from person to person. Like we do have two photographs, let it be one photograph of the size, let it be 10 by 10, one photograph of the size 1 by 1, and we are supposed to check whether these two figures or faces are isomorphic to each other or not. So we'll compare the characteristic between them: eyes, nose, ears, the comparison of ears of face, figure 1 to ears of figure 2, eyes of 1 to eyes of 2. If each and everything between them is same, we call them as identical faces, identical graphs. If we are able to find a simple one, at least one difference between two graphs or two shapes, we call them as a non-isomorphic graph. Okay, so when it comes about the isomorphic graph, we are supposed to check the common thing between them, or better to say, we are supposed to compare the characteristic between two shapes or two graphs. In terms of graph, if I am talking about, like we are supposed to check the number of edges, number of vertices, degree vertices sequence, number of vertices of same degree in the first graph to the same degree of second graph, adjacent vertices. We are supposed to check each and everything between the pair of graphs, and if we are able to find that each and everything is same between them, the graphs are said to be isomorphic. Okay, now that means what? If you are able to find the difference between them, if you are able to find at least one difference between them, we call them as a non-isomorphic graph, non-identical graph. Okay, now when we do it manually, especially when the graphs are isomorphic, it may be left with some of the characteristic. Suppose between two figures, two graphs, we compare n number of characteristics and we find they are same. And we left with one or two properties that we didn't check it. Understood? So we can't say the graph is isomorphic until unless we are supposed to check each and everything between the graphs. Mathematically, how to prove a pair of graphs are isomorphic. So for that, if suppose that we do have two graphs, let it be G and H, which is having set of vertices as V1 and V2, we call them as isomorphic graph if we are able to make a 1-1 onto mapping from the set of vertices of the graph 1 to the set of vertices of graph 2, which preserve adjacency. Adjacency means I am talking about the adjacency matrix corresponding to the mapping for the given graph. So when the question is asking to prove the graphs are isomorphic, in place of manual comparison, we are supposed to do it mathematically. And it says that if you are able to find a 1, 1 onto function from the set of vertices of graph 1 to the set of vertices of graph 2, not only 1, 1 onto function, but along with that, you are able to make the mapping such that it gives you the same adjacency matrix. It gives you the same adjacency matrix between both of them. Between, give the same adjacency matrix, not between, for both of the graph, we can say. If we are able to make a difference between them, at least one difference between them, we call that pair of graph is non-isomorphic. We call that pair of graph is non-isomorphic. Okay, to be more clear, let's take few examples on it. So this is a pair of graphs. This is a pair of graph which is given to us, and we are supposed to check whether this pair of graph is isomorphic or not. So now, as we can see, both the graph is having same number of vertices, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. If I compare the number of edges, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Same number of edges. Now I will compare. Let us check some more property like degree of the vertices. So if you see the graph H is having one vertex whose degree is 1. On the other side, there is no vertex in graph G whose degree is 1. I'm able to find one difference. What I said earlier, try to recall it. If we are able to find one difference between the pair of vertices, we call that pair of graph is non-isomorphic. So I can say, since there exists one vertex of degree 1 in H, but not in G, so the graph is not isomorphic. So the graph is not isomorphic. Are we able to find few more difference? Try by yourself. Let me give one more. This graph is having one vertex whose degree is 1, 2, 3, 4. And on the other side, this graph do not have any vertex whose degree is 4. So I can say the graphs are non-isomorphic. Okay. So when the question is asking check the graphs are isomorphic or not, we are supposed to first check the characteristic between them. Edges, vertices, degree, adjacent vertices, degree vertex sequence. If you are able to find any difference between them, we call them as a non-isomorphic graph. Okay, otherwise that pair of graph we call as a isomorphic graph. I hope you understand this example. Let us take one more example. Let us take one more example on it. So this is one more pair of graphs and we are supposed to check they are isomorphic or not. This is graph G and this is graph H. And we are interested to check they are isomorphic or not. Like you can see, they do have the different shapes. But if I redraw this graph, just take V1 here and this V4 on the top side and then V2 over here and V3 over here. What I did, I simply redraw the second graph. And now you can say they looks identical to each other. The naming of the vertices may be anything as per the convenience of the problem. And that does not matter. So now you can see between these two graphs, each and everything is same except the shape. So they are isomorphic graph. Yes, they are isomorphic graph. This is what we did it manually, like checking the condition. But how we will prove the graphs are isomorphic or not, that is also one of the important concerns. So as the definition says, a graph is said to be, a pair of graph is said to be identical or isomorphic if there exists a 1, 1 onto mapping from the set of vertices of the first graph to the set of vertices of second graph, which preserve adjacency. Preserve adjacency means what? We are supposed to make adjacency matrix for both the graph corresponding to the mapping that we constructed. If the graph is having same number of vertices, we can make n number of 1, 1 onto mapping. But it's not only about making 1, 1 onto mapping, but it is also about to check whether that mapping preserve adjacency or not. The simplest way to do it what? Redraw any one of the graphs so that it looks like same as the first graph. And then mapping can be done correspondingly. Okay, one another way to make the mapping is what? The same degree vertex should be mapped with the same degree vertex. So these are the vertices of the first graph, which is u1, u2, u3, and u4. So what is the degree of u1? The degree of u1 is 2. So it can be mapped in vertex H with a vertex whose degree is also 2. But over here, we do have all the vertices of degree 2. We do have all the vertices of degree 2. So u1 is having many choices. So let us map it with any of them. Let me map it with v1. Understood? Same degree vertex should be mapped with the same degree vertex of the second graph. Degree is one of the thing that you are supposed to pay attention on it. Now we are supposed to map it with u2. U2 is also degree 2. Yes. Now, what left in second graph? We do have v1, v2, v3, and v4. v1 is done. Now, u2 can also be mapped with any of these three because they also do have the same vertex. Now, the important point comes in the picture. What is that? If you like, it's not about the mapping. You are supposed to make a adjacency matrix too. So just remember the concept of adjacency matrix. It gives the adjacent vertices relation. So here U2 is having three choices, but to whom we will map it? Now, if your input are adjacent, your output should also be adjacent. Another important point you are supposed to take care so that you in only in one go you get the one onto mapping and the adjacency matrix same, that if your input are adjacent, then output is also supposed to be adjacent. Let us see how. So just in first graph, U1 and U2 are adjacent. Adjacent means connected by a direct edge. Connected by direct edge. So you can see U1, U2 directly connected. Now, that means their images should also be directed connected. So over here, I will write that vertex which is adjacent to V1, which is adjacent with V1. So adjacent with V1 is either V4 or V3. That means I cannot map U2 with the vertex V2, even though they do have the same degree. If you map it, you will not get the same adjacency matrix. So I'm mapping U2, let it be I'm mapping U2 with the vertex V3. So V3 is over. Now talking about U3, now in the first graph, you will see U2 and U3 are adjacent, U2 and U3 are U2 and U3 are not adjacent. If you check the first graph, in the first graph, U2 and U3, this is your U2, this is your U3, they are non-adjacent, they are not connected directly. So that means over here, I will put that vertex which is not connected to their images. So out of V2, V4, which is not connected to V3, you can say V4 is not connected to V3, V4 is not connected to V3, so this is your V4. So V4 done, what left? V2 done. So this is your 1 onto function. This is your 1 onto function. So we have generated 1 onto function, 1 onto function, which is the first part to prove the graphs are isomorphic or not. Remember it, same degree to same degree. Second thing, if input are adjacent, the output should also be adjacent. If input is adjacent, output should also be adjacent. If input is not adjacent, output should not be adjacent. In another word, we can say if input are connected, output should also be connected. If input not connected, output should not be connected. Output should not be connected. So this is 1 onto function. One of the 1 onto function. We can make n number of 1 onto function. Now, the second part of the definition, we are supposed to make adjacency matrix for the graph G and graph H with respect to the mapping. What it means by with respect to the mapping, let us try to understand it carefully. So in graph G, I listed U1, U2, U3, U4 in the same order as we did in the mapping. And for graph H, in the same order, their image exists. So U1 image is V1, so first one is V1. U2 image is V3, so V3, then V4, then V2. It's not in the order V1, V2, V3, V4. It should be in the order, it should be in the order of their images. Very important point to prove the graphs is isomorphic. What students do generally, the quite common mistake, they did it, they formulated the mapping, but when making adjacency matrix, they didn't consider the mapping and individually draw the adjacency, which is not correct. As the definition saying, what the definition saying? Adjacency matrix preserved for the given mapping. Now let us write the entries of the mapping. As I hope you know how to make an adjacency matrix. If there is an edge between the pair of vertices, it will be 1. If no edge, it will be 0. So U1 is connected to U2, U3. So U2, U3, 0. U2 in the first graph connected to 1 and 4. So 1 and then 4. U3 is connected to 1 and 4. So 1 and then 1. U2 is connected to 1, 4. U3 is connected to 1, 4. U4 is connected to 2, 3. U4 is connected to 2, 3. This is the adjacency matrix for the graph. If a pair of vertex connected, 1, not connected, 0. Understood? In the same manner, the second one. V1 is connected to V3, V4. So put it 1, 1 with V3 and V4. V3 is connected to V3 is connected to 1 and 2. So 1 and 2. V4 is connected to 2 and 1 and 2. So 1 and 2. Similarly, V2 is connected to 3 and 4. V2 is connected to 3 and 4. So what I did, I make a 1-1 onto mapping, and corresponding to that, you can say the adjacency matrix comes out as same. The adjacency matrix comes out as same. Hence, the given pair of graphs are isomorphic. The conclusion remark, there exists a 1-1 onto mapping from the set of vertices of graph G to the set of vertices graph H, which preserve adjacency. Hence, the graph or pair of the graphs are isomorphic. It's not that there's only this one onto mapping. You can make any other one onto mapping. What you are supposed to take care? You are supposed to take care same degree to same degree. You are supposed to take care if input is adjacent, output should also be adjacent. If you take care of this point, surely in one go, you will get a mapping which preserves adjacency. Hence, the graph is isomorphic. If you didn't take care of this, like input is adjacent, output is adjacent, input not adjacent, output is not adjacent, it may you are supposed to make that mapping multiple times, and every time you are supposed to check whether the adjacency matrix comes out identical or not. Understood? Let us take one more example. So this is one more example. In the shape, they looks like different. In the shape, they looks like different. And but when we compare the number of vertices, number of edges, degree of vertex sequence, everything between them is same. So now what is our task? Our task is to make a 1-1 onto mapping from the set of vertices of the first graph. So f of u1, then f of u2, then f of u3, then f of u4, and f of u5. Having 5 vertices. And do remember, when you are making mapping, none of the vertices are repeated. If you repeat the vertices, the mapping is not 1-1 onto. Understood? Now it started with the vertex u1. The vertex u1 is of degree 2. Now over here you can see every vertex is of degree 2. Yes, every vertex is degree 2. Map it with anyone. So let us, I am mapping u1 with v1. Moving to u2. U2 is adjacent to u1. So the image of u2 should be adjacent to v1. Now I can't map this V2 with U2. Why? Because you can see V1 and V2 are non-adjacent, but their images are adjacent. If image is adjacent, then output, if your input is adjacent, output must be adjacent. So what is the possibility for U2? What are the adjacent of V1? Either V3 or V4? Either V3 or V4. We can connect with any of them. We can connect with any of them, either V3 or V4. It's your choice finally. Let me make it with V4. Let me make it with V4. Now I am on V4. Moving to U3, U3 and U2 are adjacent. So the image should be adjacent to V4. What are adjacent to V4? V1 and V2. But V1 is already there in the mapping, so I should take it as V2. Moving to U4, U4 is adjacent to V3. Okay, so here image should be adjacent to V2. What are the vertices adjacent to V2? V5, V4. V4 is already used. So what left? V5. Finally, U5. Which vertex is not there? V3. So 1, 2, 3, 4, 5. So this is one of 1, 1 onto mapping, which is one of 1, 1 onto mapping, and probably it will have same adjacency matrix because we are take care of the condition. Even in few cases, you are taking care of this condition, we may not get the same adjacency matrix. In that case, we can't say the graph is not isomorphic. What we are supposed to do? Revise your mapping so that adjacency comes out as same. Let this graph is G, this graph is H. So adjacency matrix for the graph G listed the vertex U1, U2, U3, U4, U5. On this side, the same vertices in the same order, okay? U1, U2, U3, U4, U5. Now for the vertex H, A of H, it's not V1, V2, V3, V4, V5. It is as per the mapping, okay? So V1, then V4, then V2, then V5, then V3. Then V1, V4, V2, V5, and V3. Let us try to make mapping. So U1 connected to U2 and U5, U2, U5, rest entries in this row is 0. U2 is connected to U1, U3, so U1 and U3. Then U3 is connected to U2, U4, so U2 and U4. U4 is connected to U3, U5, so U3 and then U5. And last one, U5 is connected to U1, U4, U1 and then U4. Now let us see the adjacency for H. V1 is connected to V3, V4. Where is V3? This is V4, this is V3. Now V4 is connected to V1 and V2. So this is V1, this is V2, rest entries comes out as 0. Now V2 in the second graph connected to V4, V5. So this is V4 and this is V5. Then V5 is connected to V2, V3. So V2 and then V3, and similarly the last one. So now you can say I am able to make a 1, 1 onto function which gives me the same adjacency matrix. Hence, this pair of graph is also isomorphic. You can see, see it like they do have the different shapes, but still they are isomorphic. That means the second can be redrawn and it gives you the same shape as the first one. I hope you understand it. Let me check. Is there any other example? Yes, this is one more example. Try to solve it as your homework problem. Why? So that you understand the concept in more clear manner. Okay, so that's all for this session. I hope you enjoyed this session. Now, let me close it.